Visual Graph Query Interfaces, referred to as GUI, widen the reach of graph querying frameworks by enabling non-programmers to use them. Consequently, several commercial and academic frameworks, such as PubChem, for querying a large collection of small or medium-sized data graphs expose such interfaces for formulating subgraph queries. A core component of these GUI is a panel containing a set of patterns which potentially expedites visual query formulation by reducing the number of query formulation steps. In particular, users can construct multiple nodes and edges during query formulation by performing a single click and drag action in lieu of iterative construction of edges one at a time. The former is referred to as pattern at a time construction, whereas the latter is referred to as edge at a time construction. An example is the PubChem GUI, which provides a library of patterns containing benzene ring, carboxyl group, etc. The benzene structure can be constructed in a single step using the benzene ring pattern as opposed to 12 steps using edge at a time construction. Patterns on existing frameworks are typically created manually based on domain knowledge. Manual creation and selection is tedious, demands a comprehensive topological knowledge of the underlying data graphs, and limits portability of GUIs across different domains and sources, as one has to re-implement and customize every GUI. In this video, we present AURORA, a novel data-driven visual subgraph query interface construction framework for a collection of small or medium-sized data graph. In particular, AURORA exploits the underlying data graphs to automatically generate the contents of various panels in a GUI, and is designed to give end users the freedom to easily and quickly construct a visual query interface for any data source without resorting to coding. The design of AURORA is based on the following three principles, namely, work with independent graph databases, cognitive load-aware pattern selection, and oblivious to query logs. Note that cognitive load-aware pattern selection ensures patterns exposed on the GUI can be efficiently interpreted, naturally reducing the overall time a user may take to formulate a query. Oblivious to query logs allows AURORA to be used for data graphs where log data are unavailable in practice, especially in cold start cases. In practice, any graph database system can easily integrate AURORA in the following way. It can first invoke AURORA to generate the GUI for a data source and then install it on top of the query engine for query formulation and processing. The interface consists of 6 panels. Panel 1 allows user to generate useful patterns from the input data graph that supports query formulation and to load previously generated patterns. Panel 2 lists all vertex labels on the data graph. Panel 3 reports the time taken and number of steps required for formulating particular subgraph query. Panel 4 is the query construction panel. Panel 5 and 6 contain the basic and generated patterns of the data graph, respectively. AURORA automatically populates panels 2, 5, and 6. In this demonstration, we show how to generate patterns and to construct visual subgraph query using AURORA with real-world networks. In the first example, we use the PubChem dataset and configure AURORA to generate 5 patterns between sizes 3 and 7. The length of time required for pattern generation depends on the size of the data graph, the number of patterns to generate, and the pattern sizes needed. Note that this can be performed offline and the generated patterns are saved in a file that can be loaded when necessary using the Load Local Patterns button. The basic patterns in panel 5 can be configured to be of different sizes and of different numbers. Here, we set the basic patterns as 3 single-edge patterns and 2 two-edge patterns. The generated patterns can also be configured to display in different formats, such as in a single page, 4 per page, and to be grouped by size. We now demonstrate formulation of the visual subgraph query of an ethyl ester. These compounds are frequently used in the fragrance and flavor industry. We shall start by using pattern at a time approach based on the generated patterns, and then using edge at a time approach using the vertex label list. Observe that the canned patterns can be modified as desired. Here, we change the label of a vertex from C to A. The patterns in AURORA are generated to cover as many data graphs in the dataset as possible. We design AURORA to select patterns load on cognitive load to reduce mental effort by user to interpret and decide if a pattern is useful for query formulation. In addition, the generated patterns are structurally diverse patterns to make efficient use of the limited space on the interface. The pattern at a time approach took 41 seconds and required 6 steps using 3 generated patterns. Now we shall construct the query graph using edge at a time approach that is similar to commercial systems like PubChem. In this approach, we construct each vertex and edge at a time. Note that the constructed vertex are not labeled and the corresponding labels have to be assigned later. Observe that the steps in panel 2 do not account for vertex labeling and it is more than twice the number of steps taken by pattern at a time approach. Human-computer interface research shows that users may become frustrated if a large number of small atomic actions such as repeated edge construction is required for task completion. Naturally, canned patterns may also ease such frustration, especially for constructing large queries. Appropriate vertex labels are then assigned to the corresponding vertices from a label list that can be browsed. To increase usability, AURORA includes a search feature for vertex labels to facilitate fast searching of vertex labels, especially when the label list is very long and time-consuming to search through. The edge at a time approach took 1 minute and 13 seconds and required 28 steps. Hence, as demonstrated by this example, a pattern at a time query formulation can be more efficient than edge at a time formulation. Now, we shall demonstrate the portability and data-driven nature of AURORA using a different data graph. We now generate 10 instead of 5 patterns for the AIDS dataset. Observe that we use the same interface for this dataset. Similar to previous examples, we load the patterns from the saved file after it is generated. Panels 2, 5, and 6 are updated accordingly based on the input dataset. Note that the patterns of AIDS is different from that of PubChem. The common generated patterns between AIDS and PubChem are highlighted in colored boxes. In summary, AURORA provides a common framework to construct the query interface of any source and domain centered on small or medium-sized graphs. In addition, AURORA can facilitate top-down query formulation when a user has a pattern in his head to construct. Also, it can facilitate bottom-up query construction where a user can explore the generated patterns that cover the dataset and select some patterns to trigger off the process.